In this video, we're going to introduce trigonometric substitution, which is a tool we're going to use in order to simplify integrals with certain algebraic expressions. The idea behind a trig substitution is actually to introduce a trig function into the integral in such a way that it actually simplifies our function so that we're actually able to integrate it. In particular, we're going to look at how to introduce these trig functions and to make this substitution when we have an integral of a function that contains one of these three expressions, something of the form the square root of a squared minus x squared, the square root of a squared plus x squared, or the square root of x squared minus a squared, where a here is just some constant. It's some real number that we'll have in our expression. Depending on which of these three algebraic expressions appears in our function, we're going to make one of the following three substitutions. We'll either let x be a times the sine of theta, a times the tangent of theta, or a times the secant of theta, where a is that same constant that appears in the algebraic expression inside the square root. So it's no coincidence that we have three different expression forms, three different square root expressions, and three different trig substitutions that we might make. There is a correspondence between the three expressions and the three substitutions. And in order to see what that correspondence is, the best approach is to take a look at some very common trig identities and perform a little bit of algebra. So we start with three very common trig identities. 1 minus sine squared equals cosine squared, 1 plus tangent squared equals secant squared, and secant squared minus 1 equals tangent squared. Notice the last two of these identities are actually the same identity, just arranged in a different way, and both of them follow from the first one just by dividing everything by cosine squared. The key to these equations being our starting point is that on all of them on the right-hand side, we have a perfect square, either cosine squared, secant squared, or tangent squared. And the reason that's helpful is because ultimately we're going to substitute these expressions into a square root and with the goal of simplifying. And the only way to really simplify a square root is if the thing inside the square root is a perfect square. And so we want to manipulate these equations so that we keep a perfect square on the right-hand side, and then we'll be able to simplify the square root at the end of this process. Our next step is to introduce the constant a from our algebraic expression into our trig identity. Here we're going to multiply both sides of our trig identities with the constant a squared. We're going to multiply by a squared instead of a because we still want to maintain a perfect square on the right-hand side over here where we had them before. And in order to maintain a perfect square, we need to multiply by a perfect square of a constant, in this case a squared. And so we'll multiply both sides of each equation by a squared. On the left-hand side, we do distribute the a squared. And whenever we have the a squared multiplied by a trig function squared, we're going to use a property of exponents that says we could multiply a and the trig function together first and then square the product. And the result of doing this is what we have here, that a squared minus quantity a sine theta squared equals quantity a cosine theta squared, a squared plus quantity a tangent theta squared equals quantity a secant theta squared, and the quantity a secant theta squared minus a squared equals the quantity a tangent theta squared. Now that we've introduced a into each of our equations, we can take the square root of both sides for each of these equations. So for the first one, if we take the square root of both sides, the right-hand side simplifies as a cosine of theta because the right side is a perfect square. For our second equation, the right side becomes a times the secant of theta. And for our third equation, the right-hand side becomes a times the tangent of theta. And so each of these expressions simplify because the original right-hand side was a perfect square, and the square root of a perfect square can be simplified. Our final step is to actually make our substitution, and so we're going to let x equal the expression in the parentheses on the left-hand side, so either a sine theta, a tangent theta, or a secant theta. These were the three substitutions that we said we were going to make. And when we let x be each of those in turn, we can see here what the expression on the left-hand side reduces to. If x is a sine of theta, then the expression becomes the square root of a squared minus x squared. If x is a tangent theta, then the expression reduces to the square root of a squared plus x squared. And if x is a secant theta, the expression reduces to square root of x squared minus a squared. And these are the three expressions that we said we were going to use trigonometric substitution in order to simplify. And so here at the bottom of the screen, we see the correspondence between the three expressions and the three substitutions. So if we have an integral that has an expression of the form square root of a squared minus x squared, we're going to use the trig substitution, x equals a times the sine of theta. Likewise, if we have an expression of the form square root of a squared plus x squared, we're going to use the trig substitution of x equals tangent theta. And finally, if we have an expression of the form square root of x squared minus a squared, we're going to use the substitution x equals a secant theta. So let's take a look at a couple examples. Suppose we had the square root of 16 plus x squared inside an integral and wanted to make a trig substitution. To do that, we would first note that this has the form of a squared plus x squared, where a happens to be the number 4. So we get a 16 inside the square root. Based on the correspondence that we just developed, the trig substitution that we would use here is x equals 4 tangent theta. We would use 4 because that is the value of a in the radical expression. Now, the reason that we would choose this particular substitution is, as we saw before, this integral will now, or this square root rather, will now simplify nicely. So if we make this substitution in the square root of 16 plus x squared, this will be 16 plus 4 tangent theta, quantity squared, when we do that substitution. We can expand that out, so this will be 16 plus 16 tangent squared. And now both terms inside the square root have a factor of 16, so we can factor that out. And what's left is 1 plus tangent squared of theta. Now 1 plus tangent squared is equal to the secant squared by a common trig identity. It was one of the trig identities that we started with. And as we see here, that this is now a perfect square inside this square root. The square root is now equal to 4 times the secant of theta. So if we had this integral with a square root of 16 plus x squared in it, what this calculation is showing is that we can actually replace that algebraic expression, the square root of 16 plus x squared, with a much simpler trigonometric expression for secant theta. And often times we're able to integrate functions that involve these trig functions where we're not really able to do anything with the square root function as it's given. Let's take a look at another algebraic expression. Here, let's look at the square root of 100 minus x squared. So we notice right away that this has the form a squared minus x squared, where a is going to equal 10, so that we get a 100 inside the square root. And by our correspondence for trig substitution, we're going to make the substitution x equals 10 sine of theta. And when we do this, we get a square root of 100 minus x squared. This will equal 100 minus the quantity 10 sine theta squared. And like the last example, we just kind of go through the algebra and simplify this, and we'll see that we end up being able to evaluate the square root at the end. So this will be the square root of 100 minus 100 sine squared theta. We can factor out a 100 to get 1 minus sine squared theta remaining. 1 minus sine squared theta is equal to cosine squared theta by the Pythagorean identity. And so we have a perfect square inside our square root, and that's going to equal 10 cosine of theta. And so here we're able to replace the square root of 100 minus x squared with the trigonometric expression 10 cosine theta.